You have trained an amazing machine learning model. It predicts, it classifies, it generates. It is brilliant. But how do you take that brilliant prototype from your Jupyter Notebook and make it power real-world applications for millions of users? How do you ensure it stays accurate, reliable, and cost-effective over time? Hey everyone, and welcome back to BlackboardAI. I am your host, and today we are diving deep into a topic that separates hobby projects from industry-leading AI solutions. System design for machine learning. It is not just about the algorithms, it is about building the entire robust ecosystem around them. Think of it like this: a great chef can make an amazing dish, but to run a successful restaurant, you need a full kitchen, supply chain, staff, and constant quality control. The same applies to ML. So, what exactly is system design for machine learning? At its core, it is the process of architecting, building, and maintaining the end-to-end infrastructure required to deploy, operate, and continuously improve machine learning models in production. Unlike traditional software system design, which often focuses on request-response cycles and database interactions, ML system design is inherently data-centric. We are dealing with constantly evolving data, model decay, and the need for continuous learning. Why is it so crucial? 1. Scalability. Can your system handle millions of predictions per second? 2. Reliability. What happens if a data source goes down? 3. Maintainability. How easy is it to update models or fix issues? 4. Cost efficiency. Are you using resources optimally? 5. Performance. Can you deliver predictions with ultra-low latency? 6. Ethical considerations. Ensuring fairness and transparency from data to deployment. Let us break down the essential components that make up a robust ML system. This is where it all begins. ML models are only as good as the data they are trained on. Data ingestion. How do you get data from various sources into your system? Think tools like Apache Kafka for real-time streams or AWS Kinesis. Data storage. Where do you keep it? Data lakes for raw data, data warehouses for structured data, and increasingly, feature stores to standardize and serve features for both training and inference. Data transformation and pre-processing, cleaning, normalizing, handling missing values. This often involves big data processing frameworks like Apache Spark or Flink. Feature engineering, the art and science of creating new features from raw data that help your model learn better. This is a critical step for ML. Once you have your data, it is time to train. Training infrastructure. Do you need GPS? Distributed training, for example, Kubernetes Ray. Experiment tracking. You will train many models. How do you keep track of parameters, metrics, and code versions? Tools like MLflow, weights and biases, or Kubeflow are essential here. Model versioning and registry, storing trained models, their metadata, and making them discoverable. This allows you to easily roll back to previous versions if needed. Your model is trained, now let us make it useful. Model serving. How do you expose your model to users or other applications? Often via a REST API, for example, FastAPI, Flask, TensorFlow serving TorchServe. Batch versus real-time inference. Batch, processing large datasets periodically, for example, daily recommendations. Real-time, providing predictions instantly. For example, fraud detection, search autocomplete. This demands low latency and high throughput, often involving microservices, caching, and autoscaling. A/B testing/canary deployments. How do you test new models safely in production? This is often overlooked but absolutely vital. Models degrade over time. Model performance monitoring, tracking business metrics, accuracy, precision, recall, F1 score in production. Data drift. Is the incoming data distribution changing compared to what the model was trained on? This is a major cause of model decay. Concept drift. Is the underlying relationship between inputs and outputs changing? For example, what constitutes fraud evolves. Infrastructure monitoring. CPU, memory, latency, error rates of your serving infrastructure. Alerting. Setting up alerts for anomalies in any of these metrics. ML systems are not set it and forget it. They need to learn and adapt. Automated retraining, triggered by data drift, concept drift, or on a schedule. Human in the loop. for tasks like labeling new data or verifying predictions, common in fraud detection or content moderation. This feedback loop closes the learning cycle. Continuous learning. The system constantly learns from new data and adapts its models. All these components need to work together seamlessly. Orchestration. Tools like Apache Airflow or Kubeflow pipelines manage the execution order and dependencies of your ML workflows, from data ingestion to deployment. ML Ops, machine learning operations. This is not a tool, but a set of practices combining DevOps principles with machine learning. It is about automating and streamlining the entire ML lifecycle, continuous integration, continuous delivery, and continuous training for ML models. It is the secret sauce for reliable ML in production. Now, let us bring this to life with a couple of real-world examples. Imagine your favorite online shopping site. When you land on the homepage or view a product, you see recommended for you or customers also bought. This is a classic ML system. Problem: provide relevant product recommendations to users to increase engagement and sales. Data pipeline: ingestion, real-time user clickstreams, historical purchase data, product catalog updates. Storage: data lake for raw data, feature store for user embeddings, product embeddings, and real-time user session features. Feature engineering: features like users' last 10 viewed categories, time spent on product page, product popularity score. Model training: models trained on historical user item interactions. Training often happens in batches using distributed frameworks. Experiment tracking is key for A/B testing different recommendation algorithms. New models are A/B tested to ensure performance improvement before full rollout. Detecting fraudulent transactions in real time is a high-stakes ML challenge. Every millisecond counts. Problem: identify and flag potentially fraudulent transactions with high accuracy and low latency. Data pipeline: ingestion, high-volume, real-time transaction streams. Storage: transaction details in a low-latency database for feature lookup and historical data in a data warehouse. Feature engineering: critical. Features like number of transactions in last 5 minutes, average transaction amount for this user, transaction location versus user's usual location. Model training: models trained on historical labeled transactions. Handling highly imbalanced datasets is crucial. Model deployment and inference: ultra-low latency, a PI each transaction is sent to the ML model a PI for scoring almost instantly. The model returns a fraud score or a fraud/not fraud prediction, integrated with a rules engine for additional checks and immediate blocking. Retraining: continuous training, often triggered by new fraud patterns or a significant increase in false positives/negatives, to ensure the model remains effective against evolving threats. Building these systems is not without its challenges. Data quality and governance: garbage in, garbage out. Ensuring data is clean, consistent, and representative. Model explainability and bias: understanding why a model made a prediction and mitigating biases to ensure fairness. Latency and throughput: meeting stringent performance requirements for real-time systems. Cost optimization: managing infrastructure costs, especially with large-scale data and model serving. Versioning and reproducibility: being able to reproduce a model's exact state for debugging or auditing. Best practices: adopt ML Ops principles, automate as much of the ML lifecycle as possible. Start simple, iterate, do not over-engineer initially. Build a basic pipeline and then add complexity. Prioritize monitoring: you cannot fix what you cannot see. Security and compliance: essential for any production system, especially with sensitive data. So, as you can see, system design for machine learning is a comprehensive discipline. It is about moving beyond the single model to building a resilient, scalable, and continuously learning AI ecosystem. It is the bridge that transforms exciting ML research into impactful, real-world applications. Mastering ML system design is paramount for anyone serious about building production-grade AI. If you found this explanation helpful, please hit that like button, share this video with your fellow AI enthusiasts, and definitely subscribe to BlackBoard AI for more in-depth breakdowns of complex AI concepts. What other system design topics would you like us to cover? Let us know in the comments below. Thanks for watching, and I will see you in the next video.